In this video we're going to answer the first question that we asked, which was what is the shape of a hanging rope? So rather than go through the derivations, I thought I would just give you the answer first of all, and then after we've had a look at this we'll work through and we'll derive this same equation using the calculus of variations. So it turns out that the shape of a hanging rope is called a catenary, and it's given by this function here, y equals c cosh x plus b upon c. Now I've got this drawn in a graphical calculator which is available online, so I'll leave a link to this graphical calculator. I'll also leave a copy of this little equation so you can put it in the graphical calculator and you can try it out for yourself. So just to show you what these values mean, so the variable b, well the b just shifts the equation left and right. Okay, so if I just set it back equal to 0 again, we can see that the value c, well the value c is the height up off of the x-axis. For the moment there, that's value 1.3. So when we adjust c, you'll see it rising up. But not only does it rise up, also it stretches and compresses the curve as well. You can see that happening. Okay, so that there is the equation of a catenary, and we're going to go now and we'll derive it using the calculus of variations. So don't be too worried if you're not too sure about a lot of the derivation that we're going to do, because we will be working over the same types of derivation over and over again, and you will get used to it and it will actually start appearing quite easy to you. Okay, so thank you for listening and enjoy the rest of the video. So finally, let us answer the original question that we asked during the motivation video right at the very beginning. We asked what is the shape of a hanging rope. So we wanted to derive a function which defined the shape of this hanging rope. So let's go ahead and we'll do that just now using what we learned from the calculus of variations. So we have a rope hanging here over two pulleys, and we know that it hangs in such a manner to minimise this gravitational potential energy, and we were able to work out the gravitational potential energy, and this was the equation we have for it here. So if we were to simplify this, we're not interested in the function from 0 to L, we're only interested in this part of the function here. So our function f is going to be equal to 1 plus y derivative squared to the power of a half times y. Okay, so that's basically this function we have here. We also have the Euler-Lagrange equation. So if we put the value of f in here, then and we ensure that equals 0, then we're able to find the value of y, which ensures that we actually have a value for the function which is an extremum. Now we don't actually use the Euler-Lagrange equation here as is written, because in order to use this we're going to have to differentiate this function once. We're going to also have to differentiate again with respect to y derivative, and then we're going to have to differentiate 3 times, and then we're going to have to subtract one off from another. So there's a lot of work involved in that, and there is a method of simplifying it. Now the proof of this method is in a video, in a future video called the Beltrami identity. So if you're interested in going and seeing the proof of this, then you'll look up the Beltrami identity in one of the other videos. So we don't need to use this because there's no explicit dependence on x within this equation here. There's only an explicit dependence on y and y derivative. So that means that we're allowed to able to simplify the Euler-Lagrange to this simpler equation here. So it's going to be f minus y derivative partially by partial y derivative. So in this instance here, all we're going to do is one differentiation. So it makes the things an awful lot simpler. So we've got this equation here, and we've got to put this equation here into this equation here. So in effect we've got to write the function f, and then we've got to write the function, they've got to write y derivative times the partial f by partial y derivative and make that into a constant, and then we have to rejig it and try and work out what our value of y is from that. So let's go ahead and we'll do that just now. So we simply write out the function y, so the function f, so that's the function f there, and it's minus y derivative times, well now we've got to differentiate this function with respect to y derivative. Now it's actually quite easy to do that. All we're going to do is use the chain rule for differentiation. So in order to differentiate what's inside the bracket, what we do is we multiply by the exponent, so we get a half of what's inside the bracket, all to the power of minus a half, and then we have to differentiate what's inside the bracket. So we're differentiating the y derivative squared, so that's going to give us our 2y derivative. So that's us differentiated that there, and that whole thing is equal to a constant. So we still have our first term here, and we multiply our y derivative with our y derivative, so that's y derivative squared, and we have the value of our y there, and to the power of minus a half is the same as 1 over the power of a half, so that's 1 plus y derivative squared to the power of a half equals a constant. So then we're going to go and take the common factor of both of these, which is 1 plus y derivative squared to the power of a half. So we look at this and we say, what did we do to 1 to get this? We must have multiplied it by that, so we multiply this term here by that term there. So we got our y times 1 plus y derivative squared to the power of a half times 1 plus y derivative squared to the power of a half. And the top line here just remains the same, y derivative squared equals a constant. So these two here, whenever you multiply, you just add the indices. So when I add these indices, it's just to the power of 1. Anything to the power of 1 is just itself. So in the end, you just end up with the 1 plus y derivative squared times the y. So when we multiply this out, we're going to have our y plus y times y derivative squared minus y times y derivative squared there. So this one cancels out with that, and you just end up with the y upon 1 plus y derivative squared to the power of a half equals a constant. Now what we can do is we can square both sides to get rid of this power of a half, so you end up with the c squared equals y squared upon 1 plus y derivative squared. And then we can take this 1 plus y derivative squared up and we get this line here. And then we can multiply out the c squared. Multiply out c squared, we get this c squared plus c squared y derivative squared equals y squared. So not long now. What we can do is we can then take the value of our c squared down, so you get our y derivative squared equals y squared minus c squared upon c squared. So then we can take the square root of both sides, and you get the square root of y squared upon c squared minus 1. So finally we can then write that there as our dy by dx is equal to the square root of y squared upon c squared minus 1. Now we're going to put this into a standard form in order to solve this differential equation. Now the standard form we're going to have is this standard form here. So the integral of 1 upon the root of x squared minus a squared by dx, that can be written as inverse cosh x upon a plus c. So that's just a standard integral which you can get from a standard table of integrations. So if we find the reciprocal of this, that gives us this term here, and then we can multiply throughout by dy. So finally we got our dx is equal to this term here, and then we can integrate both sides of it. So when we integrate this side, we get the integral of dx, and we integrate this side here, well, we just use our standard integral up here and we replace our terms. So we'll have our x to the power of y will equal the inverse cosh of this term here, which is a y upon c, and that's all plus c. So finally we can rewrite that as y of x will equal c times the cosh of x plus b upon c, and that's what we've seen whenever we looked at the equation of a catenary in the graphical calculator. So I've sped through that relatively quickly. What you can do is take your time and read through it yourself and convince yourself of every line. And it might seem difficult at first, but you'll find out that an awful lot of these examples follow the same routes, and they all tend to use the same or very similar identities or integral identities. So once you've done 2 or 3, it'll start appearing to be relatively straightforward, but the first time you see it, it probably looks quite difficult. So that's us finally answered the question that we were looking to answer right back at the very beginning of the course. What is the shape of a hanging rope? and this is the shape of a hanging rope here, and we've derived it using the calculus of variations, and this is called a catenary. So that's all there is for this video. I'll get you on the next video. Goodbye.